Hi, I'm Anish, and today I'm going to be talking about using UNets to make segmentation masks. But first, let me present you with a problem bladder cancer. Here is a picture of a cell, part of the urinary tract, and for now, let's only focus on two parts the nucleus and the cytoplasm. In this specific kind of cell from the urinary tract, you can predict if it's malignant for bladder cancer by literally just seeing if the nucleus of the cell is like big compared to the rest of the cell. If the nucleus is big, then that means that chromosome replication has taken place too frequently and that it's probably malignant for cancer. And so we can make a diagnosis using this information by making segmentation masks. And the way segmentation masks work is by creating a mask that has a different color for the different parts of the cell. So segmentation masks basically just separate different parts of the image. So for our cell from the urinary tract here, we have blue pixels representing the nucleus, green pixels representing the cytoplasm, and then white pixels that represent the rest of the background. And using our segmentation mask, we can actually make a diagnosis. So I could say that if a cell has a certain amount of blue pixels, which represent the nucleus, of course, then that cell is malignant for cancer. So if we counted all the cells and I said something like a million pixels, if there's 2 million pixels that are blue, then I could say that it's malignant for cancer. And just looking at our picture of our urinary tract cell here, it's pretty easy just with our human eye to say that it's probably malignant for cancer with just one cell. Like if I had trained you for like 30 minutes, then as a human being, you'd probably be able to figure that out just by looking at the cell. But if instead of looking at just one cell, what if you wanted to make a diagnosis for a patient that has millions of these cells? What if I wanted to perform an experiment where like a patient would give a urine sample and then using 100,000 cells in the urine sample, I wanted to make a diagnosis if they were malignant for bladder cancer. Then I would want to analyze the 100,000 different cells. And obviously, I could not just look at those images and like a human could not just like look at the images and tell you if they were malignant for cancer or not because we can't just analyze 100,000 images just like that. So instead, what we would do is we would make a segmentation mask for those 100,000 images. And then you would do some kind of mathematical operation, like taking the average amount of blue pixels in every single segmentation mask of every single cell. And then if there's enough blue pixels or enough pixels representing the nucleus, then you could say that patient is malignant for cancer and make a diagnosis using that information. But the problem with this is that you'd have to, well, manually make a segmentation mask for every single cell, and that would just take way too long. And because of that, we're going to use units to actually make the segmentation masks. But the first step is pre-processing the image. First off, we want to make all the values from 0 to 1 because machine learning models are optimized for that. So we would convert our RGB image that has pixel values with red, green, and blue values from 0 to 255 down to a range of 0 to 1. Then we would add padding to make the image 256 by 256 so that it's a multiple of 2. And then we might want to add Gaussian blur because right now, our picture of our urinary tract cell has a lot of random like black images or black dots all around the nucleus. And as humans, we can pretty easily tell that that's not the actual nucleus. But for the model to figure out what a nucleus is or isn't, it's probably going to rely on the color of a particular pixel. And those random dark dots that are around the nucleus that are not actually the nucleus are going to be pretty confusing. So if we can blur those out, then we'll have an image that's easier for our model to understand and hopefully easier to actually segment. The unit has like two basic components, the downscaling and the upscaling component. And in the downscaling portion of the unit, we're basically learning features about the image while reducing the resolution of the image. We start out with the image that's 256 by 256 pixels. And by the bottom of the unit, we should probably be down to somewhere around 8 by 8 pixels or some low resolution image like that. And then the second part of the unit is the upscaling portion, which is the portion where we use the features we learned in the downscaling portion to generate a fully functional feature map or segmentation map that has the proper components. So our blue, green, and white pixels. The first step in the downscaling portion of the unit is convolutional layers, and these are layers that just learn features about the image. They work by having a kernel, which is the yellow box, go around the image and take the dot product of the value to find the new feature map output value. And this mathematical operation isn't really that important, but the important part to take away from this is that by doing this operation, we're able to learn features. And then we don't just use convolutional layers one time. So using our outputted convolved feature map, we would run another convolutional layer and then another convolutional layer. The first time we do this convolutional layer, the model might learn where the edges of our cell are. And then hopefully by the fifth or sixth time we use the convolutional layer, our model should hopefully know where the actual nucleus is because we want to actually make a segmentation map out of that. So our model needs to understand what a nucleus kind of is. And by applying a lot of convolutional layers, we want to be able to do that. And in addition to convolutional layers, we're using max pooling layers, which basically work to downscale our image. Max pooling layers, along with convolutional layers, make up our downscaling portion of our unit. And max pooling layers literally just work by taking the biggest value out of a set of pixels and then using that as the output. So for this example, it takes a grid of a 2 by 2 pixels, finds the biggest value, and then just outputs it. So now we've finished the downscaling portion of our unit and we have a low resolution image and we want to bring it back to our original resolution. And to do this, we're going to use convolutional transpose layers. These work by taking our initial image, which are the blue pixels, and then adding a bunch of empty pixels around them. And those pixels literally just serve to increase the resolution so that we have a new picture that is upscaled. And then we apply the convolutional layer, which I explained earlier, which has a kernel that goes around the image. And those two steps basically work to upscale our image, and it uses the features we've learned in the downscaling portion to create an upscaled image that has the proper segmentations. But these three steps alone aren't enough to make a good segmentation map. And that's because our bottom image is too low of a resolution to be able to make an accurate segmentation map. To understand this, I want you to look at the blurry picture of the Mona Lisa. If I asked you to redraw on some pixel editor or like an image editor, if I wanted you to redraw the Mona Lisa exactly perfectly pixel for pixel from the blurry image, you would not be able to do that because our original blurry image just does not have enough information. You'd be able to make a pretty good guess because from the image I'm giving you, you know where the eyes are and the hair is and like the general features of the Mona Lisa, but you don't know exactly what pixel goes where because there's just not enough information. And the model has the same issue. At the bottom of the unit, the image is just at a too low of a resolution to be able to figure out what goes where. And to fix this, we use merge skip connections, which basically allow the model to use previous feature maps, as can be seen from the arrow in our unit here, to be able to preserve some of the more minute details. And then by doing this, our feature map should be able to be accurate down to the pixel instead of just being some inaccurate guess that's has a pretty big margin of error. After making our model, we have to make some post-processing adjustments to it to ensure that it's an actual usable segmentation map. Generally, machine learning models output values of 0 to 1, but to make it an image, we need to make it values from 0 to 255. And then during the pre-processing, if we added any padding, we should remove that. But the most important part of the post-processing step is to make sure that our cell is, or to make sure that any issues with the UNet are pretty much just fixed. So for this example with bladder cancer, the segmentation map that my UNet model predicted had this issue where it would have a bunch of random blue pixels all over the place. It was able to get the general features right, so because the new unit was able to figure out where the nucleus of the cell was and where the cytoplasm, because you can like generally tell where those things are. But there's a bunch of random blue pixels, and so for my specific problem, I was able to fix it by just adding some Gaussian blur. But depending on what kind of issues you might have after running your model, you might have to use different post-processing techniques to fix those. And after that, you should hopefully have a fully functioning segmentation mask UNet model that is able to make a segmentation mask, which you can then use to make some kind of diagnosis, like bladder cancer in this example. Thank you for listening.